this time, we're not doing anything new, no new theory. All we're gonna do is we're gonna look at this problem and we're going to define all of these quantities. So first of all, what's the problem? We've got a rod pinned right here. This rod is connected to a slider. So I'm going to highlight in blue. Here is a sliding block. So the blue block slides in the groove, and then the groove is in this rod. This rod is pinned as shown, and also inside of the groove here, there is a spring attached to the blue block, okay? So this first one is going to spin round. As this one spins round, this pin joint here connected to this block is going to make this block, right? It's gonna move with this first rod. And as it does, it's going to slide in the groove and it's going to make this rod rotate as well. So here are the things that we want to define for this problem. We want linear momentum for the whole system, angular momentum. I have these subscripts here, JJ. What I'm saying here is I want the angular momentum of A about A, B about B, C about C. I want kinetic energy for the whole system. I want potential energy for the whole system. I want sum of forces. Again, I use this subscript J. This means I want sum of forces on A, sum of forces on B, sum of forces on C, right? I want sum of moments J about J. So again, sum of moments A about A, B about B, C about C. If we want these quantities, what here in the problem do we have to define? If we want to do linear momentum, that means we need centers of mass. So let's put centers of mass on here. This first rod, let's call this rod A. So I'm going to put center of mass here at A. Let's make this part down here on the block. Let's make this easy for us. Let's say that it is pinned right through the center of mass. Let's call that center of mass B. So this slider, block B. And then this slotted rod is C. Now, where's the center of mass here? We don't actually know. It's going to depend on geometry and all kinds of things. So I'm just going to put one arbitrarily, let's just say right here. And that's fine. I could put it at the bottom. I could just as easily have put it somewhere along the top. The location of it is going to be symbolic anyway, so it's going to work out. We have centers of mass. We need to find the velocity of those points for linear momentum. For angular momentum, we need to define the inertia of the bodies, or at least have some knowledge of it. We also need angular velocity. So linear momentum, linear velocity. Angular momentum, angular velocity. Kinetic energy, we actually need linear and angular velocity. So if you can do these first two, if you can do linear and angular momentum, you can do kinetic energy. Potential energy, remember that potential energy is a function of position. Kinetic energy is a function of speeds. Potential energy will be a function of position. So for gravitational potential, we need position vectors to centers of masses. And then there's definitely going to be some force associated with the spring. Sum of forces and sum of moments, we have three bodies, A, B, and C. I expect three free body diagrams. Free body diagram of A, B, C, fully annotated, and then you write these expressions. And as many details as I give you in the problem, I need you to include all of those details here. Now, I'm going to put a question mark up here at the top, and I'm raising it as a question. Do we need to define constraints? And do we need to define degrees of freedom? What we're going to do is let's do all of this, and then when we get some final answers at the very end, we're going to come back and we're going to talk about what effect constraints and degrees of freedom would have had on this analysis. So while we have this up here, let's go ahead and put some quantities here on the diagram. We know that to do linear momentum, we're going to have to do velocity of these points. So we need some distances. Now, we could assume that point A is right in the middle of this first link. It doesn't have to be. We could do one length, L1, and let's put point This is point N. So the length from N to A is L1. We could say that the length from N to B is L2. Again, this doesn't have to be perfectly in the middle. Let's say that this distance is, and let's call this one point D. So D to C, remember C is I just kind of picked a place for C. It's not the bottom of the spring, it's not the bottom of the slide, it's the center of mass. So it is somewhere here on the length. We're just going to call this L3, and clearly the block moves up and down. So that's a variable, that one's going to be Q. L1, L2, L3, and Q. Hey, little Deb. We've got all the lengths, L1, L2, L3, and Q. What other lengths? Well, there's some offset, right, between point N and point D. Definitely if we were going after the constraints, we would need this offset. So here is L4 in the vertical. Here is L5 in the horizontal. Beyond this, what else do we need? Frames. We've got points, frames. So here is the non-moving inertial frame. We have 3 bodies. We need 3 frames. I'm going to put a frame right here. And we're saying this is the XY plane. So here is X hat in, Y hat in. This would be XA, this would be YA. So the same thing now for this body. We can see that block B and the slotted rod C, these are actually going to rotate with the same angle. They each have a frame, B frame, C frame, but the frames rotate together. So I'm going to say XB on top, YB, nope, not YB, XC. There we go. So there's XB, there's XC. Here is YB, YC. Before we do momentums, let's go ahead and do angular velocity. We have omega into A, omega into B, and omega into C. We need to define all 3 of these. Looking at the diagram, there's only 2 rotating frames, A frame and B frame. Let's say that A, the A frame, we're going to connect, we're going to attach theta 1 to the A frame, and we're going to attach theta 2 to the B frame. Both of these are rotating about the Z-axis. And then omega into C, well, this is actually the same thing as B, right? These 2 things rotate together. So I can say omega into C equals omega into B, and I can bring this down. Theta 2 dot ZB. Good. Put these in the notes, keep them. We're going to need them in a second. We said we wanted linear momentum of the system. K of the system. What is linear momentum of the system? Well, we had 3 bodies, A, B, and C. So K of the system is K of A plus K of B plus K of C. We can come down and we can just call these out. This is MAVA, which is MA DDT of P and A. This is MA DDT. So what should we call out P and A? I've erased it, but in your notes you should have the diagram. For P and A, I'm going to say L1X at A. We've had a lot of practice. We know that this is going to be MA L1 theta 1 dot Y at A. There's KA. KB. So point B is at the end of the first rod. So this is going to be MB VB. This is MB DDT of P and B. Let's call P and B L2 X hat A. Okay, so KB is MB VB, MB times L2 theta 1 dot Y hat A. So here's Ka, here's Kb. Let's do Kc. Standard definitions apply. Kc is MC Vc. What is Vc? This is d dt of P into C. MC ddt. How should we call out point C? You could either go into B, B to C, or we could do into D, D to C. So I'm going to do into D and then D to C. This was L4 in the YN. This was negative. L5 in the XN, and then L3 in the XB. Go back and look at the diagram. All I've done is I went from N to D through two offsets, and then I went from D to C going up in the X hat B direction. So Kc is, we take d dt of this, these are constants. MC, we take d dt of this one, L3, theta 2 dot, YB. There we go. So put this one down in your notes, keep it. That is it for linear momentum. Next, let's talk about angular momentum. We said we wanted HJJ. Now when I say HJJ, again, what I mean is I want HAA, HBB, HCC. This is just one way of writing the angular momentum of a body about its own center of mass. AA, BB, CC. Notice that I'm not asking you to add them all together. I'm not saying HAA plus HBB plus HCC. I'm also not asking for angular momentum of the system about a particular point. All I want right now, each individual angular momentum. Let's take HAA. We have the definitions for these. We know that this is IAA, omega NA. Recall that IAA, this is the inertia dyadic. It's the inertia of body A about point A. What does this look like? Dimensions of these, IAA is a 3x3 and omega NA is a 3x1. That makes HAA also a 3x1. This is a matrix or dyadic. We have some idea of what it looks like. It's a 3x3. We're going to make an assumption that body A is symmetric. If body A is axisymmetric, then these off-diagonal terms will all go to 0. Now, what about the diagonal terms? You could look these up in a table, right? If I give you mass, I give you lengths, all of this, you can look up the equations in a table. For now, I'm just going to say this is, here is IXX, here is IYY, here is IZZ. Are these all the exact same number? Not necessarily, it depends. It depends on geometry and mass. You're the engineer, you design this part inside of CAD software. The CAD software, you give it material properties, you give it geometry, it'll tell you this quantity. So this is your IAA. Again, we don't know the specifics, we're just generalizing it. What about omega NA? I'm going to draw omega NA as the 3x1 vector. You have it in your notes what it is. This was 0, 0, and then theta 1 dot was here. So this is HAA, here is IAA, here is omega into A. We perform this multiplication and we get, I'm going to say IZZ comma AA, so this is the IZZ term out of the IAA matrix. That way we can keep it separate between bodies. But it's this IZZ term multiplied by multiplied by theta 1 dot, and it acts in the Z hat A direction. Don't forget, HAA is a vector. We need to keep these directions on here. Now, again, what is this? You get it out of a formula sheet or something. Right now, we're not worried about it. It's just some number. So here's HAA. If we're going to do HBB and HCC, how different is this process? If you can do it for one, you can do it for the other. So write this one down in your notes. Here's HAA. Let's go and let's do HBB. I'm just going to erase some of these indices. HBB equals IBB omega n to b. Same equation every time. Here is a general 3x3 matrix representing inertia. This could just as easily represent IBB as it represented IAA a second ago. Here is omega n to b. Omega n to b, the only difference here is this one does not rotate with theta 1. It rotates with theta 2. So HBB is this multiplied by this. We can come down and we can modify this answer. So IZZ from the BB matrix multiplied by theta 2 dot, and just to keep it consistent, it's rotating around ZB. So I want HCC as well. HCC is the slotted rod. Does that change anything? No. This is the equation every time. So HCC for this problem is going to come out as IZZ CC. Omega n to c is also theta 2 dot, and this is in the ZC direction. Now, is it always this simple? No. More complicated problems, more complicated geometry, for example, this matrix isn't in actual objects, this eraser, this pen, this cat tower. None of these objects are perfectly axisymmetric, so these off-diagonal terms, they're not actually zero in real problems. Also, you can be rotating about multiple axes. There's no guarantee that you're just doing a simple rotation all the time. So always go back to your original equations and then put in the terms for the specific problem, and if it comes out nice and simple, okay. But if it's more complicated, you can handle that too, right? Right? I said we wanted T of the system. Again, remember T is kinetic energy. If we want T of the whole system, that means we need the kinetic energies of every single body, and then we add them together. This is TA plus TB plus TC. If there was a DEF, it'd be plus DEF. Let's take each one of these individually. TA. So the kinetic energy of A. We have an equation for kinetic energy. 1/2. Let's say VA dot KA. It's a good way to put it. Remember the dimensions of energy. It's a scalar, right? This is not a vector. So we take a 3x1 vector and we dot it with a 3x1 vector, and we get a scalar. This is a convenient way to write it because we have already defined both VA and KA. Plus 1/2 omega into A dot HAA. Again, this is a convenient way to write it because we have already defined these quantities. So what all does this come out to be? Okay, I'm going to pull out the 1/2. I'm going to put a set of brackets around the whole thing. We have VA dot KA. This is, I'm going to write these as vectors for this first part, just to show the dimensions. We said a few minutes ago this was L1 theta 1 dot. L1 theta 1 dot. This was in the y hat a direction, right? So nothing in the x, nothing in the z, velocity in the y. We're dotting this against 0 ma L1 theta 1 dot. Y hat a 0 plus, so we'll just say dot 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 for now. So this is just this first term, right? Here's the linear velocity of the center of mass of A. Here is the linear momentum of body A. So this is a real easy dot product, right? We're looking at 1/2 and MA L1 squared theta 1 dot squared. And that takes care of this. If you are concerned about units, we know the units of energy are joules. This is going to be kilogram. Here is meter squared. Here is 1/second squared. Kilogram meter squared per second squared. So this is a joule. Next, let's do the second half. So I'm going to say dot, 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 representing the first part that we just took care of, plus, and let's bring this down. Well, we could do like we did a second ago, and I could draw these as vectors. I could also just bring these terms down, and we could just do the dot products. This is theta 2 dot ZA, and then we're doing a dot product with, this was IZZ from AA, sorry, this is theta 1 dot, IZZ AA multiplied by theta 1 dot ZA. So we're doing dot product. So we have a ZA and a ZA term. These are going to turn into a scalar. We have the inertia term, IZZ AA, and multiplied by the theta 1 dot squared. We're doing kinetic energy at B now. I've taken the exact same equation. I've just erased out the subscripts. I've put in B. Let's drop in the specifics and see what we get. So 1/2 VB dot KB. You should already have this in your notes. This is going to be L2 theta 1 dot YA dotted against MB L2 theta 1 dot YA. And then plus dot, dot, dot. We will take care of the second term in a second. Here at the bottom, TB is equal to, we can resolve this very quickly. This is a 1/2 the scalar mass in B L2 squared and the angular speed theta 1 dot squared. That takes care of this first term. Let's do the second term. All right, I put in the ellipsis. There's the linear portion of energy, and then we're adding, we got the 1/2 here. It's going to be omega into B. We said that was theta 2 dot ZB, and we're dotting against HBB. We did this a minute ago. This was IZZ BB theta 2 dot ZB. And brackets. All right, we just do this dot product, right? Bring down the scalar inertia term, IZZ from BB, bring down the angular velocities, and close it off with brackets. We could also look at this one in terms of units if you're concerned about units. The units of inertia are kilogram meter squared. The units of the angular velocity, radians per second. So this becomes 1/seconds squared. Kilogram meter squared per second squared. This one's also a joule. Okay, interesting point on this one. Notice that this energy, it's a function of theta 1 dot and also theta 2 dot. This expression has two of the generalized speeds in the expression, theta 1 dot, theta 2 dot. Now, if you went back and you looked at the original problem, there's only 1 degree of freedom, which means if you had done the constraints, you could, at this point, you could use the constraints to replace theta 2 dot in terms of theta 1 dot, and now your expression for TB is all in terms of the input speed. All right, here's your TB. Put this in your notes. Let's do TC and then we'll move on. So now kinetic energy of C. TC 1/2 VC dot KC 1/2 omega into C dot HCC. Let's put in the specifics. TC is 1/2. Let's do this first one. This was L3 theta 2 dot YB dot L3 theta 2 mass MC L3 theta 2 dot YB. So we can do this dot product, bring down the scalar mass, MC L3 squared theta 2 dot squared. Oh, 1/2. Don't forget the 1/2. So there's the linear portion, the angular portion, bring down the ellipsis, 1/2 is here, theta 2 ZB. Tell you what, we're doing C, we can put this one in the C frame, keep it consistent. Dot IZZ from CC, theta 2 dot ZC. You can leave it in terms of ZB, it's fine, it's the same thing. Perform this dot product, we have this scalar inertia term that comes down, IZZ, CC, theta 2 dot squared. Okay, so here was TC. You already have TA and TB. If you want the total kinetic energy, you add all three of them together. We've got this done. Let's do potential energy next. Next, we're doing potential. We want potential energy of the whole system. What is the potential energy of the whole system? Well, there were three bodies, and the bodies are moving, so in a general sense, they could have potential. So let's get these written down. Remember, we're using the Greek letter phi, depending on how you want to say it. And I'm saying that each body, A, B, and C, has their own potential. I'm letting these represent gravity. There is also the spring, and springs can have potential energy. So phi for the spring. Let's do the three gravitational potentials first. If I say phi A, the gravitational potential associated with A, we know there is the equation mgh. We did talk in class before spring break about how this is actually an approximation. What we're going to do in this semester is we're not going to worry about how gravity changes with position. We're going to do m, okay, mass of A multiplied by g, and then in place of h, we're doing vector systems. So we need a more robust way of calculating it. Let's do P in A dot y hat n. We're saying that gravity acts in the y hat n direction. What we need is the vertical displacement. So we're already tracking all of these centers of masses because we did linear momentum. So we just take those position vectors and we do a dot product, and now we have our gravitational potential. So MA multiplied by G, we need P and A. This was L1 X hat A, and we're dotting it with Y hat N. If you're going to do the dot product, you have to be in the same frame. We know that we can rotate the A frame. We could define this A frame in terms of the N frame using our standard rotations. So what this becomes is MAG times L1 times sine theta 1. Here's another thing that is convenient. Because we're doing the dot product, this was a vector, and we're taking the vector and we're dotting it against a vector. This is just a unit vector in the y hat n direction, so it's still technically a 3 by 1. But once you do the dot product, it becomes a scalar. And remember that energy, here is phi A. Remember that energy is scalar. So MA times G times L1 times sine theta 1. Now, maybe you could just look at the problem and you could sort out that this was it. That's fine. You don't have to do all of these intermediate steps, but when the system becomes very complex, these steps are still always true. So if you have position vectors to centers of mass, you sort out the frames, you do the dot product, and here's your energy. So there's the potential associated with A. Let's do the potentials with B and C. The potential associated with B, same story. MB times G. We're going to do P into B dot Y hat N. This is MB times G. P into B, we did L2 X hat A, yeah, dot that with Y hat N, okay. So the potential associated with B is MB G L2 sine theta 1. Good. Next, let's do potential associated with C. VC, this is going to equal MC G P into C dot Y hat N. Okay? We need our description of what we did P into C. So this was negative L4 Y hat N plus L5 X hat N plus L3 XB, right? That's what we did for P into C. We went from point N through offsets to the other pin joint, and then we went up from the pin joint to that center of mass. Okay, so when you perform the, and it's that dot Y hat N. Okay, when you perform this dot product, what happens? You can take each of these, we could distribute the dot Y hat N. So it's this first term dot Y hat N, the second term dot Y hat N, third term dot Y hat N. Clearly Y hat N dot Y hat N is 1, so we're going to end up with MC times G. There's going to be a negative L4, this one's going to be 0, and then this frame we're going to have to rotate the B frame into the N frame. So we will end up with L3 sine theta 2 minus L4. And here is our potential associated with body C. Okay, we've got this. Let's do potential with the spring. Potentials with springs. We have an equation for it. I gave it to you in class. This is going to be 1/2 K. I'm just going to write it as 1/2 kx squared. And this is just a general expression of it. What are these terms? Well, this, the K, this is a spring constant. This has units of newtons per meter. Next, this X represents the displacement. So in this particular problem, what is all of this going to come out to be? So I'm just going to say phi sub s, so phi of the spring, it is 1/2 K, K is whatever K is, and then we need this displacement. So we could write it as Q squared, and that's how much the block is displaced. What if the block had some nominal length? Like what if the spring has a certain length unloaded? Here's how you modify it. I'm going to open up the parentheses. I'm going to say Q minus Q sub naught. So again, this sub naught, this is the initial length. And then you square the whole quantity. It's not Q squared minus Q naught squared. It's the whole quantity, it's the change in position, and it's that quantity squared. We could go up to this equation, and just to make that a little more clear, I'm going to say that this is delta x squared. We want to do sum of forces and moments. If we're going to do those, the first thing we need to do is a free body diagram for each individual body. Body A was the input crank, body B is the sliding block, body C is the slotted rod. Each one of these gets their own free body diagram. Let's start filling it out. Simple things first. We know that gravity is acting on each one of these. I can do a gravity vector. Here's MAG, here is MBG, and somewhere in here, acting through the center of mass, is MCG. Good, next. Let's say that, next let's deal with the pin joints. So there's going to be reactions at these pin joints. I'm going to put R1 right here on this first one in the bottom left. Now, R1 is broken actually into two components. There's R1 in the X and R1 in the Y. We'll get to that in a bit. If there's reactions at this pin joint, there's reactions at the second pin joint as well. So here is R2. And also, let's say that if this is the input crank, let's say that there's some motor acting on this system that's also inputting a torque tau. So tau is being applied at on this body here. So next, body B. We said that body B is the sliding block. Clearly gravity is acting on it. What else is acting on it? Consider that block B interfaces with both body A and with body C, right? There's a pin joint that is the interface between A and B, and then there is the groove that is the joint between B and C. There's reaction forces here at this pin joint. So look at how we define the reactions. I did them to the right and I did them up. This is my personal style. You need to develop your personal style. If I do positives here, I'm going to do negatives over here. So again, it was positives on body A, that means negatives on body B. If this is R2, this is also R2. And this is Newton's third law. This is action-reaction. So there's gravity, there's R2, there's also the joint between B and C, which is the groove. So let's think about that groove. It allows some motion. It allows the block to slide. So there is no restriction, there is no constraint in the groove direction. However, you can't take the block and you can't arbitrarily move it left and right. Also, you can't arbitrarily spin it. So what keeps the block from moving left and right? Well, if I grabbed the block and I moved it left and right, it would push against the rod and the rod would rotate with it. So there is there's the constraint between B and C that the groove enforces, and what is going to keep this block from arbitrarily moving is some reaction on these bodies. So I'm going to draw this reaction like this. I'm going to call this one, this was 2, let's call this R3. So R3 is it's like a normal force. It's gonna prevent this block from going left and right. Now, I also mentioned that this block cannot arbitrarily rotate. If C rotates, then B rotates with C, right? They had the same rotation, same angular velocity. What that means is, what makes this rotate? That means there is a moment, and I'm going to call this one, let's call it R4. R4 it's a reaction moment. So there's a reaction moment between the block and the slotted rod. When the slotted rod rotates, the block has to rotate with it. And if you have a change in angular momentum, if there's some angular acceleration, there has to be a moment to bring that about. So we go from B now to C. Don't forget Newton's third law. Here is R3, and I drew it to the right. That means somewhere acting on here, on this body C, here is R3. Next, there's the reaction moment associated with that groove. I drew a positive moment. That means I need to draw a negative moment on this body. So here's R4. And finally, there is a pin joint at the bottom. Here is R5. R1, X and Y, R2, X and Y, R5, X and Y. R3 is in one direction only, R4 is a moment, and then we also have input torque and 3 masses. In this problem, I am going to make one simplification. For this problem, we are not going to include any friction. So I think this is good for the 3 free body diagrams. Make sure you have this in your notes. Next, I'm going to clean this up and let's start writing down sum of forces and moments for each of the individual bodies. I've redrawn the body A free body diagram. I put it small, I put it in the corner, but it has R1, it has R2, and then it has gravity. So let's come and let's define sum of forces. We can just list these things out. We know there's gravity, we know there's R1, we know there's R2. When we define gravity, clearly the gravity is acting in the negative y hat n. I can say minus mag in the y hat n direction. What are we going to do with R1 and R2 though? In the last example we did these pin joints in the end frame. Let's do something different. This time, let's put it in the body frame and let's see what happens to it. So I'm going to come here to the top. I'm going to say there's gravity, and then there is also R1x and R2x. These act in the x hat A. And then there is R1y and R2y. These act in the y hat A. So again, R1 and R2. I drew both of them positive on body A, so it's positive, 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 positive. And we're going to put these in the body frame, and let's see what difference it makes. This is acceptable for sum of forces. And this is all the forces. Some of them can be in inertial frame, that's fine. Some of them can be in body frame, that's fine. So sum of forces on A, you're done. Next, sum of moments on A about A. Oh, and I forgot this input torque tau. There we go. We get down to sum of moments on A. The input torque tau we can immediately bring down. There's tau. This is acting in the positive z hat A direction, right? Gravity creates no moment about center of gravity because that's where it acts. We do have to worry about the moments created by R1 and R2 though. I'm going to do a general expression. I'm going to say, remember the names of the points. The point in the middle, this was point A. Down here, this was point N in the left. And in the top right corner, this was point B. So we need position vectors. We need the position vector from A to N. And then we're going to cross the forces that act at point N. That's R1x, x hat A, R1y, y hat A. Next, we need the position vector from A to B, and we're going to cross that with R2x, xa, R2y, ya. Let's sort out these position vectors. Then we can resolve the cross products and we'll be done with some moments on A. We've actually done A to N already. A to N this is equal to negative P into A. And then PA to B, I can put in what this is. This is minus, PA to N is going to end up being negative L1 x hat A. And then PA to B. A to B, we did the distance into B as L2, and we said that maybe point A is not perfectly in the middle. That means the position vector from A to B is L2 minus L1 in the x hat A. I'm going to simplify this. This was negative L1 x A. Okay. So we want sum of moments. I'll put this one in blue. Sum of moments A about A. I'm going to bring down our input torque. I'm just going to write it here as tau. Let's perform these cross products. Here is negative L1 x hat A cross a term in the x hat A and a term in the y hat A. We can distribute the cross product. So x hat A cross x hat A, that's going to go to 0. X hat A cross y hat A, okay, we can perform that. what's going to happen? Well, the scalars are going to be negative, right, because there's a negative here, and then it's x cross y, which is positive z. So we're looking at negative L1 R1 y, and that's going to be in the z hat A direction. Tau is in z hat A. I'm just going to group these things together, and we'll put z hat A at the end. Next, this cross product. We have L2 minus L1, that's just a scalar. Don't worry about it being complicated. It's x hat A cross. Here's a term in the x hat A, here's a term in the y hat A. Again, same thing happens. X hat A cross x hat A, these are zeros, right? And then x hat A cross y hat A is positive z. These scalars end up being positive this time. It's going to be this multiplied by that. So I'm going to say plus L2 minus L1 multiplied by R2y, and it is this whole quantity in the z hat A direction. Input torque, this is the reactions at point N, and then here is your reaction at point B. Now, we were able to get that in this problem, and it came out nice and simple. And what really made it simple was here, when we defined those reaction forces in frame A. Now, that's not always a good idea. You could work a different problem where you're putting them in the body frame, makes it fairly complicated. We're going to see what happens in body B, why in this case it wasn't a bad choice. Here's the free body diagram for B. Remember, there's gravity. R2 is negative, it was positive on body A. R3 is the normal force that keeps the block in the groove. R4 is the reaction moment that maintains the orientation of the sliding block with respect to the slotted rod. And also, let's not forget, there is also a spring force. I'm going to call that Fs. So we have all these on the free body diagram. Let's just write out the math equations now. So we have sum of forces on B. Let's just take each of these and bring them over. Let's start with gravity minus mbg in the y hat in direction. Next, let's do the reaction 2, this set of reaction forces. They were positive on body A, so they are negative here, so minus R2x. And remember, these were in the A frame, so they're still here in the A frame when we come to this body. So R2y, y hat A. Good, next. R3. R3 is this normal force that keeps it in the groove. There is no component of R3 in the groove itself. That means it acts in the B frame, and if you go back to the original diagrams, we set the B frame up like this. Here was XB pointing up, and then pointing to the left was YB. When I did the free body diagrams a minute ago, I just arbitrarily picked right for this one. Right is in the negative y hat B direction, so this is negative R3 YB. And next, the spring force. We don't know if the spring is under tension or compression, so at this point we just pick a direction. You could just as easily have drawn the arrow up, that's fine too. I've drawn it down, so I'm going to make it negative, so let's do minus Fs in the XB direction. And again, you go back to the frame, you can see that I've put the spring force in the negative XB direction. So this is it. We've got all kinds of frames in play. We've got in frame, A frame, and B frame. Again, this is acceptable. If we wanted to numerically sum all these up, and I wanted to know the value, the sum of forces in each of the three directions, clearly we would need to put all of these in the same frame and then add them up. Next, we want to do sum of moments on this. We want the sum of moments on B about B. Well, look at the diagram. How many of these forces even create moments? We helped ourselves out a bit during the setup. We made some assumptions. We said that the pin joint was right through the middle, which means R2 acts at the center of mass, which means it creates no moment. By definition, gravity acts at the center of mass, it creates no moment. If we attach the spring force, right, along that same line that contains the center of mass, if we model this, this normal force as on the center, the geometric center of this plate, that puts it right in line with the center of mass as well. None of these forces create any moments. The only moment then in the problem is just this, this reaction moment R4. So R4 in the ZB. What are the implications of this? Understand that the sum of moments on B is not zero. R4 is not zero. This exists. When the slotted rod rotates, the block has to rotate with it, right? There's no local rotation between them. So in order for this block to rotate, there has to be a moment making it rotate. And here is that moment. Here's the Freebody diagram for body C, the slotted rod. We have reaction set 5. These are positive. We have the spring force. Remember, it was down on the sliding block, so it's up on the slotted rod. Gravity, R3 and R4, I reversed the directions from body B onto body C. I've also added the C frame, and I've added these two lengths. Remember, this was point D, point C, point B. So we have L3 is from D to C, and Q is from D to B. So let's do sum of forces on body C. So for sum of forces, remember, we're just going to take these and bring them over. We can start with gravity minus mcg in the y-headed direction. Next, we've got let's do the spring force next. So spring force now is pointed up, plus Fs, and this is acting in the yc direction. Next, let's do reaction set 5. So these are positive. This is R5x in xc and R5y in yc. Next, we have R3. So R3 is pointed in the positive yc direction. So I'm going to say plus R3 in the yc. So we've got gravity, spring force, R5, R3. We still have R4, but remember that's a reaction moment, not a reaction force. So this is good. This is everything that's on the diagram. Here we have it. We have it in different frames, which is fine. We have in frame blended with C frame. Next, let's do sum of moments on C about C. So from the diagram, which of these forces create moments? Gravity, of course, does not. Spring force, notice that the spring force, if we assume that the spring, the attachment is aligned with the center of mass, then this will create no moment either. We do have to worry about the moment created by R3 and the moments created by the reaction forces. So let's put those in there. I'm going to take R4 and I'm going to copy R4 over. Remember, positive rotation is this way, so this R4, it's a negative rotation, minus R4 in the ZC direction. For these two, I'm just going to add some general expressions. So let's say plus the position vector. So let's do R3. It's the position vector from C to B, cross the forces acting there. So this was R3 in the YC direction. Next, let's find the moments associated with these reaction forces. We need the position vector from C to D. So I'm going to say PC to D. Excuse me. Cross, and we need these two reaction forces. So it's R5X, not XA, this is XC, there we go. And then plus R5Y in the YC. Good. Let's sort out these position vectors. PC to B, so from C to B. Well, if this distance is Q, and if this distance is L3, clearly the PC to B, this is going to be Q minus L3, and this is in the XC direction. So that was PC to B. Next, PC to D. So here is C, here is D, the distance is L3, and we're going against X hat C. This one is negative L3 XC. So here was the general. Here are the specifics for these position vectors. Let's resolve the cross products. And let's see what we get. So I'm gonna copy the negative R4 ZC. We can bring that up. Here is the moment caused by R3. The position vector is here. It's in the XC direction. We're crossing it with the YC direction. X cross Y is going to yield a positive Z. So I'm just going to add the scalar components. It's Q minus L3. Again, that's just a number multiplied by R3, and this is in the ZC direction. If you look at how R3, we know which direction it acts in. It acts in YC. Look at where we attached it. We could attach it here at this blue point. We could attach it here at point B. I did the position vector, I did this position vector, C to B. What if we had done the position vector from C to B and B over here to this point on the side? That would have added to this position vector, it would have added some component, I'm just going to say L, some component in the YC direction, right? If we had considered it acting at this point instead, we would have still done the same cross product. We would have had X plus Y cross Y. And of course we can distribute the cross product, and then the Y cross Y would have been 0. So when we look here at R3, it actually doesn't matter which of these 2 points we attach it at, we end up with the same moment. Next, let's do this last piece. So we have a position vector here, it's negative L3 XC. We can distribute the cross product. So it's X cross X, that's going to be 0. X cross Y, this is going to be Z, X. So X cross Y is Z. There is the negative in front. So I'm going to make this negative, and then we'll multiply the scalars. L3 R5Y, X cross Y is Z. So there are your 3 moments on body C. We have the reaction R4, and that comes from the block. We have R3, that was this normal force. Interesting, notice that this one is a function of Q, so as the block slides in the groove, the moment changes. And then here we have the moment created by this reaction at this pin joint. Good. So this problem was it was a little longer. We did both momentums. We did kinetic and potential energy, and then we did forces and moments. Next videos, we're going to do some more problems where we do a full write-up through forces and moments. A couple more examples with those. I've also been promising y'all a discussion on friction, so I'll upload a video just on friction. And in the next couple of days, I need to put a video up talking about conservation laws. So just be aware, all these things are coming at you. We'll see you in the next couple of days. Until then, stay safe, wash your hands.